All right. Next, we are going to talk about sort of picking up where we left off from the previous video, but what we talked about in example 2, and we are going to talk about the definition of convergence of an infinite series. So what does it mean for an infinite series to converge? So remember that an infinite series, something like this, is really just a sum where we're adding up infinitely many things. So when we talk about convergence, we really mean to say, when does this even make sense? Because if we have some sort of series, like let's look on the previous page, this series. Does the series converge to a finite number or diverge? Well, if you think about it, if I just start adding up these numbers, 2 plus 4 plus 6 plus 8 plus 10, just if I'm adding up all the even numbers, is this going to equal some finite real number, some fixed number? No, not at all. Each of these numbers is getting bigger, and we're adding it. There's no negatives. They're all positive, and the numbers are getting bigger, so this series will equal infinity. So we would say that this series here diverges to infinity, i.e., this series from n equals 1 to infinity of 2n is equal to infinity. So sometimes it's very easy and clear to see whether a sum diverges or not. Other times it's not so clear. Understandably so, if we're adding up infinitely many things, then if each new thing we add on is bigger than the previous things, definitely that sum's going to diverge. But what if the pieces that we're adding up are actually getting smaller, such as is the case up here at example 2, 1 over 2 to the n is our general term. So we are really adding up things. So if I just write this out, this is 1 plus a half plus a quarter plus an eighth plus a 16th plus, ooh, it's terrible, 16, plus a 32nd, so on and so forth. These terms are getting smaller. They are getting smaller. So one thing we can do, sort of like a first order way of talking about convergence, is to look at estimations of the sum. Right? That's a natural thing to do. If you have some numeric quantity and you don't know its true value, because calculating its true value seems to be an insurmountable task or sufficiently difficult, what you can do is try to estimate things. Much like how you did in Calc 1 with, if we have a function, say y is a function of x, and you want to know the graph between here and here, whatever these two x values are, let's say x equals a and x equals b. If you wanted to know what this area is, a natural thing to do would be to split this region up into some rectangles. And the answer that we're going to get using these rectangles is not going to be perfect. Clearly we can see that this part here is an overestimate, and then even here we have some underestimates. This rectangle here, the third one, seems to do a pretty good job. That's because the curve is pretty flat right here. But yeah, we start with a certain number of rectangles, let's say 4, and we'll get an approximation. And if that really isn't good enough for us, then we can take it a step further and we can tack on more rectangles. We could subdivide these rectangles. Instead of having 4, we can have 8. And we can make that number of rectangles as large as we want, which will give us a finer and finer and finer estimate to the true value. Well, we can do the exact same. We can basically do the same idea, but it doesn't have to do with areas, really. And that is, if we have some series, such as this one here, and this goes on forever, if we wanted to get an estimate for this and try to make sense of it, we would just add up not all infinitely many terms, but maybe 5 terms, 10 terms, 20 terms, 100 terms, and see if these seem to be getting closer to a fixed number. So what we can do is use partial sums, and that's exactly what a partial sum is. It's giving us an estimate for the sum. So if we do the the partial sum where we're only looking at the first term of the sum, we get like a 0th order approximation. It's not that great. We get the number 1. So now we look at the next degree of accuracy, the next partial sum, we get 3 halves. Okay, so 3 halves, okay, it's changed. Next we get 7 fourths. Okay. For the third partial sum, we get 15 eighths. So to put it into perspective here, let's just write down what these are as decimals. So down here, we've actually already written this out, and we found a pattern in the partial sums. But if we take a look at these as decimals, of course, 1, 1.5, and then 7 fourths is 1.75. 15 eighths is 1.875. Now, we didn't include this next one, but the next one would be, we would have 16, and then 16 doubled is 32, minus 1 is 31. So 31/16, what's that? That's 1.9375. And then the next one would be 32 and then 63 30-seconds, which is 1.9685. So you can see that all these decimals, these decimal expansions of the fractions, they all are getting bigger each and every time, but the progress, so the amount that one term of the sequence, so the amount that it increases by, that difference in 2 terms is getting smaller. So here, the jump is 0.5. Here, the jump is 0.25. Here, that jump is what? What's 1.875 minus 1.75? That's 1.2, it's 0.125. Okay? So here it jumps by a half. Here it jumps by a quarter. Here it jumps by an eighth. And here it jumps by, I believe this would be a 16th. And this jumps by a 32nd. So the amount that we're increasing by, so the difference between successive terms of the sequence, that difference is decreasing. So that essentially means these numbers here are going to get they're going to bunch up. They're going to sort of get closer and closer and closer and closer to some specific number. And if we had to just guess a general trend as to where these numbers were growing, what numerical value is being approached, we would probably argue that this appears to be approaching the number 2. So we can treat each of these partial sums as an estimate for the true sum. It doesn't take us very long to see that the true sum is about 2. Now, if you're not convinced by this, you could take it a step further. You could take a look at any power of 2. Any power of 2. So let's say 512. That's a power of 2. And then I can double that and get 1024. So this would be 1023 over 512. So what's 1023 divided by 512? That is 1.99804 and yada, 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 yada. So 1.99. So it doesn't take very long to convince yourself that this is, the sequence appears to be converging to the number 2. So the limit as n goes to infinity of s sub n appears to be 2. Now, what's nice is this kind of sequence, this kind of sum, and therefore this kind of sequence, is it is actually easy and possible for us to obtain an expression for S sub n. It's not always possible or easy to find an expression for this S sub n. Sometimes this is extremely elusive, at least to write it down in closed form. But because in this case it is possible and we did find it, we can actually take a look and calculate explicitly what the limit of this is. So the limit of this nth partial sum is the limit of this 2 times 2 to the n minus 1 over 2 to the n. Well, here we can use the method of dominating terms. The dominating terms are 2 to the n in the top and 2 to the n. So if I use the method of dominating terms, this is just the ratio of the coefficients. So 2 over 1, which is 2. So this sequence of partial sums does indeed converge to the number 2. And this is exactly what we're going to use as the definition of convergence of an infinite series. So given some infinite series, and that series converges to this sum S, we will say this whenever the sequence of its partial sums converges to S. So in this way, we define convergence of an infinite series to be the convergence of the sequence of partial sums, which is a really sort of complicated way of saying an infinite series sums to a finite number when we take successively or increasingly accurate estimations for the sum, and those estimations all appear to be approaching the same number. So in other words, if you estimate your sum again and again and again using more and more terms, if those estimates all appear to be honing in on a specific number, then that's the number we say the series converges to, and that's the sum of the infinite series. So if that's the case, then we can just say that series equals that number S, the limit of the sequence of partial sums. If the limit doesn't exist, we say the series diverges. If the limit of this is infinite, we say the series diverges to infinity.